morning to all. Today I am going to take lecture on fiber reinforced composite materials, challenges and opportunities. So I am Dr. R Satheesh Raja, Professor, Department of Mechanical Engineering, PSN College of Engineering and Technology, Tirunelveli. So today material plays an important role in all the innovation and development of the manufacturing sector. So in the Indus Valley civilization itself, our ancestors used different types of materials for making weapons, ornaments and for transports. They used wood, then iron, copper, brass, bronze. So in the recent years, we switched over to the new term composite materials. Particularly in the composite material, fiber reinforced composites. Here I am going to give brief introduction about fiber reinforced composites. Before that, we will see what is meant by composite. So a composite is a material composed of two or more materials at a microscopic scale and have chemically distinct phases. So in the composite material, at least we need two different materials at a microscopic scale. It is heterogeneous at a microscopic scale, but statically homogeneous at macroscopic scale. So if you view the composite material by using any microscope, for example scanning electron microscope, then transmission electron microscope, we can able to see the materials, two distinct materials. It is in heterogeneous scale, but in a product, it is in a macroscopic scale. It is a constant materials having significantly different properties. So we are having two different materials in that composite. The two materials having two different properties. At a whole, as a composite material, you will get unique property by the combination of these two materials. Then classification of certain materials as a composite. Combination of materials should result in significant property changes. This is the main reason we go for composite material. If you want to enhance certain property, then you have to add the correct proportions in the composites, whether it is a reinforced material or matrix material. Then content of the constituents is generally more than 10%. In general, property of one constituent is much greater greater than equal to 5 than the other. So in our history, we used the composite material as a different products. This is the oldest application existence of composite material. In 4000 BC, laminated writing material from the papyrus plant. In 1300 BC, Egyptians and Mesopotamians used straw bricks. 1200 AD, Mongols invented the first composite bow. This is the best example for composite material which was occurred in ancient days itself. Composite bow dates back to 3000 BC, Angara dating Here materials used wood, horn, sinew, leather, bamboo and antler, that is deer horn. Horn and antler naturally flexible and resilient. That is the main property in the horn and antler. Then sinews, back, tendons or hamstrings of cows and deer. Then glue from bladder of fish, strings, sinew, horsehair, silk. So these are all the materials involved in the composite bow. These are all naturally available materials and composite material. The evolution of material. So starting from iron, copper, then cast iron, steels, alloy steels. Nowadays we are using composite for the advanced development in the industrial sectors. So examples from day-to-day life. So for example, straw, mainly to enhance the desired properties in the product, we go for composite materials. Some of the desired properties are listed below: strength, stiffness, toughness, corrosion resistance, wear resistance, reduced weight. The main advantage of using composite compared with the alloys and other materials, you can able to get the desired property, and also the reduce will also reduced, weight will also reduced. That is the main advantage. So weight reduced, then overall cost, the efficiency will increase. That is the main advantage of using composite materials compared with the other materials. Then fatigue life, thermal, electrical insulation and conductivity, acoustic insulation, energy dissipation, attractiveness, cost. So these are all the desired properties are increased or enhanced by using composite materials. There are two main constituents in a composite material. First one is reinforcement. This is the main one. It is in discontinuous nature, and stronger one and harder. Then matrix. Matrix are mainly used to hold the reinforcement materials and to protect the reinforcement from environment. It is continuous one. These are all the functions of a reinforcement: to contribute desired properties is the main function, and also to carry the load and to transfer the strength to matrix material. Then functions of a matrix. We are going to see about the functions of a matrix. Already we discussed about the functions of a reinforcement material. Matrix are mainly used to hold the fibers together, whether it is glass fiber or carbon fiber, metal fiber, ceramic fiber. It is mainly used to hold the fibers and to protect the fibers from environment, protects the fibers from abrasion, helps to maintain the distribution of fibers, then distributes the loads evenly between fibers from one fiber to another fiber, then enhances some of the properties of the resulting material and structural component. These properties such as transverse strength of a lamina, impact resistance, then provide better finish to final product. Then based on type of matrix material, they are classified composites as polymer matrix composites, metal matrix composites, ceramic matrix composites, carbon and graphite composites. Then again polymer matrix composites are classified as thermoset and thermoplastic composites. composites. Then based on the form of reinforcement, we are classifying composite as fiber, viscous, flake, particulate. So fiber is a filament with length to diameter ratio is very high, in the order of 1000. Then composite with fiber reinforcement is called fibrous composite or fiber reinforced composites, or it is called as FRP or GFRP, that is glass fiber reinforced composites. Then particle, non-fibrous with no long dimension. So when compared with the fiber, particle is negligible dimension one. Almost it is one dimensional one. Then a composite with particles as reinforcement is called particulate composite. Then viscous, nearly perfect single crystal fiber. Short, discontinuous, polygonal cross section. Then based on the form of reinforcement, the previous one we discussed about based on the reinforcement material, whether it is fiber, viscous. Here in the form, based on the form of reinforcement, continuous fiber and discontinuous fiber. Then continuous fiber is divided into unidirectional, woven, discontinuous fiber, random oriented, preferred. Then woven is classified as bidirectional, dimensional. Then bidirectional is classified as single layer. Then based on the form of reinforcement, again they are classified into random orientation, preferred orientation. So for better load transfer from matrix to fiber composites require large surface area of the fiber matrix interface. It is calculated by using the calculations. Capital A is equal to capital N by dl, where N denotes number of fibers present in the composites, D diameter of the fiber, L length of fibers. If the fiber diameter is smaller, then capital D is replaced by small d. For same fiber volume fraction, small n is equal to capital N into capital D by small d whole square. Then for new fiber matrix interface area, capital A is equal to n pi d square L divided by d which is equal to 4 into volume of fibers divided by small d. Thus for a given fiber volume fraction, area of the fiber matrix interface is inversely proportional to the diameter of the fiber. Then fiber volume fraction and matrix volume fraction is related in terms Vf plus Vm is equal to 1. That is, Vf indicates the volume of fibers in composites, Vm volume fraction of matrix in composite. The fibers should be flexible so that they can be bent easily without breaking. For example, woven fiber composites need flexible fibers. Flexibility generally is defined as inverse of bending stiffness. For example, consider a fiber as being under pure bending, then EA is equal to bending stiffness or flexural rigidity. Flexibility is directly proportional to 1 by EA, where I is equal to pi d power 4 by 64. Thus, flexibility of a fiber is inversely proportional to 4th power of the fiber diameter. So in the previous chapters we have discussed about the conventional fibers used in the fiber reinforced composites. Now we are going to see about what are the advanced fibers are nowadays used in composite materials. Fibers possessing high specific stiffness and specific strength. For example, glass fiber, carbon fiber, organic fiber, ceramic fibers comes under this category. Then natural fibers, apart from synthetic fibers, nowadays research are going on in natural fibers. So by using natural fibers instead of synthetic fiber, the main advantage is it is eco-friendly. It will not affect the environment, and also cost-wise it is very cheap when compared with synthetic fiber. It's naturally available one. Only thing is you have to process these fibers before we are going to manufacture composite materials. You have to chemically treat the natural fibers to make it use in the composite material production. Some of the natural fibers available are, first category is animal fibers, that is silk, wool, spider silk, sinew, camel hair or comes under animal fibers. Then vegetable fibers, cotton, jute, bamboo, sisal, maize, hemp, sugarcane, banana, rami, kapok, kaya, alpaca, flax, neem, raffia, palm are all vegetable fibers. Then mineral fibers, asbestos, basalt, mineral wool, glass wool are mineral fibers. This table indicates the types of fibers and conventional metals. Then advanced fibers. In this first one is glass fibers. It is commercially used one in all category, in all the fields. Nowadays they are mostly using glass fibers because of availability and it is in economic one and also having desired properties. So in ancient Egyptians made containers from coarse fibers drawn from heat softened glass. It is produced by extruding molten glass at 1200 degrees centigrade, and also it passed through spinnerets of 1 to 2 mm diameter, then drawing the filaments to produce fibers of diameter between 1 to 5 micrometer. The individual filament is small in diameter, isotropic in behavior and very flexible. In the glass fiber we are having different varieties based on their properties. First one is the E-glass fiber. It is having high strength and high resistivity. Then S2 glass, high strength, modulus, stability under extreme temperature, corrosive environment. Then R glass, enhanced mechanical properties. Then C glass, resist corrosion in an acid environment. D glass, dielectric properties. So if you want to produce any component, then you have to choose the reinforcement glass materials, glass fibers according to the property needed in the or property required in the product, particular product. If you want high strength means we go for glass fiber. If you are using that product in corrosive environment means then we go for C glass fiber. So based on the application of the product, we can choose the glass fibers. In general, glass fibers are isotropic in nature. Another fiber is carbon fiber. It is also advanced one. Carbon-carbon covalent bond is the strongest in nature. So Thomas Edison made carbon fiber from bamboo when experimenting for light bulb. Then what is the difference between carbon and graphite fibers? So based on the percentage of carbon present, they are classifying as carbon fiber and graphite fiber. For example, in graphite fiber, it contains more than 99% carbon, but in carbon fiber it contains 80 to 95% of carbon. Carbon fiber is produced at 1300 degrees centigrade, while graphite fiber is produced in excess of 1900 degrees centigrade. So in general term, carbon fiber is used for both fibers. So these fibers are made of two types of precursor materials: polyacrylonitrile, rayon pitch. Precursor fiber is carbonized rather than melting. The filaments are made by controlled pyrolysis, that is chemical deposition by heat of a precursor material in fiber form by heat treatment at temperature of around 1000 to 3000 degrees centigrade. These fibers are having different morphologies, origin, size and shape. The morphology is very dependent on the manufacturing process. So based on the what type of manufacturing method we are using, their morphology will also vary. The size of the filament ranges from 3 to 14 micrometer, hence it is very flexible one. Maximum temperature of use of the fibers ranges from 250 degrees centigrade to 2000 degrees centigrade. Properties changes with temperature at high temperature. The maximum temperature of use of a composite is controlled by the use temperature of the matrix. Modulus and strength is controlled by the process thermal decomposition of the organic precursor under well controlled conditions of temperature and stress. Thus carbon fibers are anisotropic in nature. Then another fiber is aramide fibers, that is aromatic polyamide, that is family of nylons. Polyamide 6 equal to nylon 6, polyamide 6.6 equal to nylon 6.6. It is spun from a liquid solution. Morphology: radially arranged crystalline sheets resulting into anisotropic properties. Its diameter around 12 micrometer and partially flexible. It has high tensile strength, intermediate modulus, very low elongation up to breaking point, significantly lower strength in compression. DuPont developed these fibers under the trade name Kevlar. It is called, in commercial it is called as Kevlar fiber. It is manufactured from polyvinyl terephthalamide, that is PPTA polymer. In Kevlar, 5 grades are available for various engineering purposes to meet the required properties. That is Kevlar 29, Kevlar 49, Kevlar 100, Kevlar 119, Kevlar 129. So So these are the 5 grades of Kevlar. Then ceramic fibers, that is boron fiber. It was the first advanced fiber developed for structural application in 1959 by Talley. It is also called the ceramic monofilament fiber. It is manufactured by using chemical vapor deposition method onto a tungsten core of 12 micrometer diameter. Here fiber itself is act as a composite because we are having boron and tungsten material. It is circular in cross section. Its diameter ranges between 33 to 400 micrometer and typical diameter is 140 micrometer. Boron is brittle, hence larger diameter results in lower flexibility. The thermal coefficient mismatch between boron and tungsten results in thermal residual stresses during fabrication cool down to room temperature. It is normally coated with silicon carbide or boron carbide, can be used to reinforce light alloys. It is strong in both tension and compression property. It exhibit linear axial stress strain relationship up to 650 degrees centigrade, but the protection cost is high when compared with the other fibers. Another ceramic fiber is alumina Al2O3. These are ceramics fabricated by spinning a slurry mix of alumina particles and additives to form a yarn which is then subjected to controlled heating. The fiber retains strength at high temperature. Another ceramic fiber is silicon carbide SiC. Here the two methods are used to synthesize silicon carbide. First one is chemical vapor deposition on tungsten or carbon. Carbon pyrolytic graphite coated carbon core SES6. This fiber is similar in size and microstructure to boron. Relatively stiff, size of 140 micrometer. In the second method, controlled pyrolysis, chemical deposition by heat of a polymeric precursor. The filament is similar to carbon fiber in size approximately 14 micrometer, more flexible. Silicon carbide shows high structural stability and strength retention even at temperature above 1000 degrees centigrade. Then we will discuss about the cross-sectional shapes of fibers. So based on the cross-sectional also, the property will also change. And the finishing product quality will also vary based on the shape of the fibers. First one is circular cross-section. Examples: glass fiber, carbon, organic fibers, alumina, silicon carbide are comes under circular one. Then elliptical, alumina, then mullite, triangular, silk fiber, silicon carbide, viscous or triangular in shape, hexagonal, Al2O3, rounded triangular, Al2O3 single crystal fiber, kidney bean, carbon fiber, trilobal, carbon rayon. So with this we have discussed about the different types of fibers available, that is natural fibers, synthetic fibers, then advanced fibers, and also what are the methods available to synthesize the fibers and the cross-sectional area of the fibers. Now we are going to discuss about the types of materials used in the polymer matrix composites or fiber reinforced composites. Polymers. So in these two main types, thermoplastic and thermosetting. The thermoplastic is softened upon heating and can be reshaped with heat and pressure. So we can able to reshape the thermoplastic products by means of heating and applying the pressure. Most of the household products are made of thermoplastic only. Then thermosetting, it's opposite to thermoplastic. It is cross-linked during fabrication and do not soften upon preheating. So while applying the heat and pressure, it will not change the dimension, it will not change the shape. That is the main difference between thermoplastic and thermosetting. Then other types of matrix materials, metal also used as matrix material. If we are using metal, then we called metal matrix composites. Then ceramic matrix composites. If we are using matrix as ceramics, then the composite is called as ceramic matrix composites. Then carbon and graphite. If you are using carbon matrix and carbon fiber means, then carbon composites. Then some of the thermoplastics materials are polypropylene, polyvinyl chloride, PVC, that is PVC, nylon, polyurethane, polyether, ether ketone, PEEK, PEK, polyphenol sulfide, PPS, polysulfone. Mostly thermoplastics are higher toughness zone, high volume, low cost processing, temperature range greater than 225 degrees centigrade. Thermoplastics are increasingly used over thermosets because of the following reasons. The processing method is very faster when compared to thermoset composites, because no curing reaction is required for thermoplastic. But for thermosetting we need long curing process. Thermoplastic require only heating, shaping and cooling. Then better properties, high toughness and damage tolerance, low moisture absorption, chemical resistance, and also they have low toxicity, but only thing is cost is high. Then some of the thermosets matrix materials are polyesters, epoxies, polyamides, other resins. First one is polyesters. When compared to other epoxy materials, polyester is very cheapest one, and also having good mechanical strength, low viscosity, versatility, good electrical properties, good heat resistance, cold and hot molding, curing temperature is around 120 degrees centigrade. Another matrix material is epoxy material. In the most of the advanced composite material products, they are using epoxy resins because of its high strength and flexibility, then low shrinkage during curing, better electrical properties, and also resistance to chemicals and solvents, better adhesion between fiber and matrix. Because of this adhesion property, the formation of voids are avoided during the manufacturing of composite material by using epoxy as a matrix material. The disadvantages of using epoxy matrix: somewhat it is toxic in nature, and the limited temperature application range up to 175 degrees centigrade. Then moisture absorption affecting dimensional properties, high thermal coefficient of expansion, then slow curing. Then another material, polyamides, having excellent mechanical strength and also withstand the strength in the range, temperature range 260 to 315 degrees centigrade. Then having excellent electrical properties, good fire resistance and low smoke emission. Curing temperature is around 175 degrees centigrade and 315 degrees centigrade. Then what are the problems facing while we are using polymer matrix composites? So limited temperature range. Main thing is the temperature range is very limited. Then low transfer strength. So the polymer matrix cannot be used near or above the glass transition temperature. Then another matrix material, metal matrix. Mostly aluminum, titanium, copper are used as a matrix material, as a metal matrix material in composites. Aluminum matrix composites use temperature range above 300 degrees centigrade and titanium at 800 degrees centigrade. When compared with the polymer matrix, metal matrix composites are suitable for high temperature applications. It's also having higher transfer strength, toughness, the absence of moisture and high thermal conductivity. Disadvantages: heavier the weight is high when compared with polymer matrix. More susceptible to interface degradation at the fiber matrix interface and to corrosion. So another matrix material is ceramic matrix. Carbon, silicon carbide and silicon nitride are used as ceramic as a matrix in ceramics matrix composites. When compared with the metal matrix composites, the usage of ceramic matrix composite in the high temperature range greater than 2000 degrees centigrade. So it is very suitable for high temperature applications, high elastic modulus, then it's having low density, it is having brittle nature. So another matrix material is carbon. Carbon is also a fiber and also matrix. So it's called as carbon fibers in carbon matrix is called as carbon-carbon composites. Both the fiber and matrix materials are carbon. It's used under extreme mechanical and thermal loads. For example, in space we need strength also to withstand thermal loads. So it is mainly suitable for aerospace applications. Advantages: low specific weight, high heat absorption capacity, resistance to thermal shock, high resistance to damage, exceptional frictional properties at high energy levels, resistance to high temperatures, chemical inertness, low coefficient of thermal expansion. Only thing is low resistance to oxidation above 500 degrees centigrade, high cost of materials and manufacturing. Fiber and carbon cost is high and also manufacturing cost is also high. These are all the different types of fiber and matrix materials and their properties: density, physical properties, density, modulus, mechanical properties, strength, Poisson ratio, specific stiffness, specific strength, thermal expansion coefficients. The first one, first three row denotes the metal matrix, then fibers, then matrix materials. First one metals, pure metals, steel, aluminum, titanium, then fibers, next matrix materials. Then forms of fibrous composites, mostly the layered composites are used for manufacturing the composite materials. It is also called as layer, lamina, ply. Any one of the term is used in the composite material manufacturing method. Axial and transverse. Axial means the fibers along the fiber length. The composites are along the manufactured along the fiber length. Transverse means perpendicular to fiber length. Two in plane transverse, out of plane transverse. Layered composites. So in the layered composites, the fibers are placed layer by layer. Then you have to apply the matrix material at each layer. Then you have to go for curing process. Then we will get the composite material. In the layered method, we are having three types of layer, different types of layer. First one indicates the plane, second twill, third one setting. These are the three methods of placing the fiber in the manufacturing of composite materials. Then fiber and matrix systems. So fiber / matrix. Fiber is the reinforcement material. Matrix is the holding material in the composites. For example, carbon epoxy. Carbon is the fiber. Epoxy is the matrix material. In glass epoxy, glass is the fiber. Epoxy is the matrix. Kevlar epoxy, Kevlar fiber in epoxy matrix. The proportion of contents must be mentioned by using volume fraction. That is, Vf plus Vm is equal to 1. Examples: AS4/peak, T300/5208, T700/M21, IM8/epoxy, Kevlar/epoxy, up to IM8/AX is called as carbon composites. Then Kevlar epoxy, boron, aluminum, SES silicon, 6Ti titanium, S2 glass fiber in epoxy matrix. This table indicates the properties of fibrous composites, different properties for different materials. In the first column we are having density, physical property, mechanical property, thermal property, then volume fraction. Second one, composite material, one type of composite, AS4 3501, like that, up to S2 glass epoxy fiber. So reduction in properties compared to reinforcement properties. Axial along fiber length, transverse perpendicular to fiber, degree of orthography. Then we are going to discuss about the parameters affecting the properties of fibrous composites. Length of the fiber. In the short length fiber we are having long length fiber or particulate fiber. Based on the length also, the composite strength will also vary. Then orientation of the fiber. In which angle we are placing the fiber, that will also plays an important role in the transfer of load in the composite material. Then shape of the fiber, based on the cross sectional shape, whether it is circular, triangular, rectangular one or hexagon. Then distribution of the fibers in matrix material. Then properties of fibers, properties of matrix material, proportion of fiber and matrix material. Mostly the matrix material proportion is greater than the fiber volume fraction. Then based on the user requirements, performance requirements, total production volume, these are all fabrication process. How to make the composite material. There are different methods available for manufacturing composites. So based on the application, based on the dimensions, based on the cross section we are needed, we go for or we are selecting the fabrication method. These are the factors affecting the fabrication processes. User requirements, performance requirements, total production volume, production rate, cost of production also play important role, size of the production, surface finish of the final product, geometry of the product, material. So more than 50 processes depending upon the fiber matrix type and nature. We are going to see some of the processes involved in the manufacturing of composite materials. That is wet hand layup method, spray layup method, vacuum bagging, filament winding, pultrusion, resin transfer molding, braiding, vacuum assisted RTM, centrifugal casting. So these are all the important processes involved or used for making composite product. So based on the factors already we have discussed, we have to choose which method is suitable for manufacturing the composites. So this figure denotes the process involved in wet or hand layup method. It is a very simple method. We can able to make any type of shape by using this method, and cost wise it is very cheaper when compared with other methods. In this we are having one simple mold, then one roller. So in the mold you have to apply the gel coat before we are going to apply resin. Then you have to apply resin. So in the resin, the surface of the resin you have to place the fiber, whether it is in fiber mat or individual fiber. Then you have to uniformly distribute the fiber along the surface of the matrix. Then you have to give pressure by using the roller. Then only you have to avoid the formation of voids in the composite material. Like that you have to apply the matrix, then fiber up to the required dimension is reached. So up to the required dimension is reached, you have to continuously apply the matrix and fiber. Then you have to give pressure by using roller. Then spray layer, it's similar to hand layer method. Instead of applying resin in manual manner, here we are using pressurized, pressure controlled spray that will avoid that is over usage of resin, and it will control the uniform distribution of resin over the surface of the fiber and also in the surface of the mold. Then vacuum bagging, here also we are using release coated mold, vacuum bagging film. Here we are supplying the materials by we are supplying the laminate in the mold, and by we are cooling, where we are curing the composite material after applying the matrix and fiber material, we are curing the process by creating the vacuum in the system. That is the main difference. Then filament winding. This method is mainly used for making the hollow cylindrical pipe, composite pipe. Then pultrusion. It's also used to make the channels or rectangular cross section pipes. Then resin transfer molding. Here we are using upper mold and lower mold. So in between the mold we are supplying the resin and fiber. Then you have to apply pressure at the top of the upper mold. Then braiding. Braiding is mainly used for making carbon-carbon composites. Then centrifugal casting. Then we go for applications of fibrous composites. It's mainly suitable for high temperature applications like in aerospace, military. Then in civil engineering also we are using fiber reinforced composites for making electronics items. Then panels, solar panels. In automobile for structural applications, sports, medical equipments for making medical equipments, marine sector to prevent the corrosion resistance. In aerospace, for example, use of composites in light compact aircraft gauges. Here they are used different colors. So in blue color indicates in that part they are used glass composites, glass fiber composites. In the nose section they used Kevlar composites. In the wing section they used aluminum, and 80% of the components are made of carbon composites. Use of composites in helicopter. Here also they are used different colors. Each color indicates the individual separate composite material. For example, orange color indicates the Kevlar composites, blue color indicates the carbon composites, black color indicates the carbon glass composites, green color indicates the glass fiber composites. The helicopter blade, it's also made of composite material. The automobile for transportation. These are some of the sports items. In cycle, structural elements, hockey stick, helmet, gloves material, racket. So wind energy, in the wind blade they are used by using composite material only because of its low weight and high strength. These are all medical applications. Then civil structure they are using, instead of steel they are using glass fibers. In marine, disadvantages of composite materials. The main thing is high cost of raw materials and fabrications, and also it is very brittle in nature, so it is easily damageable one. Matrix is weak, therefore low toughness, and reuse and disposal may be difficult. Health hazards during manufacturing, curing and after use, and also joining two parts is difficult. In metal and alloys, For joining two metals, we are having different methods: rivet joint, welding joint. But in composite materials, it is very difficult to join parts. Then repair introduce new problems for the following reasons. Materials require refrigerated transport and storage and have limited shelf life. Hot curing is necessary in many cases, requiring special tooling. Curing takes time. Analysis is difficult. Matrix is subject to environmental degradation. These are all the disadvantages of composite materials. Then natural fibers, we already discussed about this. Animal fiber, spider silk, protein fiber, cotton fiber, diameter 12 to 20 micrometer diameter, length around 10 to 60 mm length. These are vegetable fibers. Comparison of properties of different natural fibers: cotton, jute, hemp, sisal, coir. So with this I want to conclude this topic, fiber reinforced composites. Here we have discussed about what is meant by composite materials. What are the composite materials already our ancestors used around 3000 years back, and what are the composite material naturally available like wood, human body. And we discussed about different types of fibers, different types of matrix, then different types of composites also, and properties of composite, then different types of methods used to manufacturing the composite materials. I think this will be useful for those who are studying basic things about composite materials, and also useful for researchers involved in composite materials. Thank you, one and all.